Let's take a look at the solution of this initial value problem. So in this problem, we have a forcing function that has jumps. So we'll notice that there's a jump of size 5 that occurs at time pi. And then at time 2 pi, there's a jump of size 5 going downwards. So minus 5 u of 2 pi of t. And so that's the way to express the function f of t in terms of these unit step functions. So taking the Laplace transform of this top equation, we get that s squared y of s minus s times y of 0 minus y prime of 0, Laplace transform of y double prime, plus the Laplace transform of y equals the Laplace transform of the right-hand side. So 5e to the minus pi s over s minus 5e to the minus 2 pi s over s. Okay, so applying the initial conditions, this part is 0, this part is 1, so I'm going to bring that over to the right-hand side. S squared plus 1, y of s, equals 1 plus 5e to the minus pi s over s minus 5e to the minus 2 pi s over s. Then dividing by s squared plus 1, we get that the Laplace transform of the solution is 1 over s squared plus 1 plus 5e to the minus pi s over s squared plus 1, then minus 5e to the minus 2 pi s over s times s squared plus 1. And so now we have to figure out the inverse Laplace transform of this. All right, to do this, we will temporarily ignore the e to the minus pi s up here and just simply focus on the remainder. So we have 5 over s times s squared plus 1. And the partial fraction decomposition will be a over s plus b times s plus c over s squared plus 1. Okay, so 5 is going to be equal to a times s squared plus 1 plus s times b times s plus c. And for this one, it's actually fairly straightforward to do this by just simply matching the coefficients. A plus b times s squared plus c times s. Then I have a plus c as the constant. I'm sorry, just a is the constant. I apologize. And so we could quickly see that the constant a matches the 5 here. There's no 0c over here, so c is equal to 0. Also, there's no s squared over here, so b will be equal to negative 5. Okay, so we get that this is equal to 5 over s, then minus 5 times s over s squared plus 1. And that is the decomposition for 5 over s times s squared plus 1. Okay, just FYI. So this you didn't have to do in this problem, but I just want to point out. We could also consider this function as 5 over s times 1 over s squared plus 1. It's the product of two Laplace transforms. And so therefore the inverse Laplace transform of this can be considered as the integral from 0 to t of the inverse transform of this is 5. Well, actually, I'm going to do this one first. The inverse transform of this one is sine of u. The inverse transform of this is 1, and I evaluate the function 1 at the point t minus u du. And so this works out to be negative cosine of u evaluated from t to 0. And then plugging in the endpoints, I get 1 minus cosine of t. And I'm sorry, I forgot the 5. There's a 5, not 1, so minus 5. So 5 minus 5 cosine t. That's indeed what I see here. If I take the inverse Laplace transform, I get 5 from this constant minus 5 cosine t. So the inverse Laplace transform, whether I do it by partial fractions, I see I get 5 minus 5 cosine t, or I could do it by convolution, and I get 5 minus 5 cosine t. So therefore, the inverse Laplace transform of 5 over s times s squared plus 1, if I put in the extra e to the minus pi s, that's going to be equal to 5 minus 5 cosine of t minus pi times the step function at pi. Likewise, the inverse Laplace transform at 5e to the minus 2 pi s over s squared plus 1. It's going to look an awful like the same, 5 minus 5 cosine of t minus 2 pi times the step function at 2 pi. So I've got all the pieces. So there's my function y of s. And so y of t is going to be equal to, the inverse Laplace transform of this is sine t. The inverse Laplace transform of this is 5 times 1 minus cosine of t minus pi times the step function at pi. And then this last part is going to be minus 5, 1 minus cosine t minus 2 pi times the step function at 2 pi. And so that's the answer. I'm sorry, made a dumb mistake here at the top. So y of 0 in the problem was given to be equal to 1, so this should have been an s here. I apologize. So that's an s, and so this becomes a cosine. I apologize about that. Okay, so that is our final answer. Now, just to make this a slightly more explicit, let me break this up into parts. This is piecewise defined. I have one answer if t is less than pi. I have a second answer if t is between pi and 2 pi. I have a third answer if t is greater than or equal to 2 pi. Now, if t is less than pi, both of these are 0, and I end up just with cosine t. If t is between pi and 2 pi, then the bottom one is 0, but the top two still count. So I end up with cosine t plus 5 minus 5 cosine of t minus pi. And then if t is greater than or equal to 2 pi, then all terms count. So I get cosine t, then plus 5 minus 5 cancel, and I have minus 5 cosine t minus pi from the top, and then minus a minus plus 5 cosine of t minus 2 pi from the bottom. And I wouldn't necessarily expect this on the exam, but using trig identities, this can be written significantly more simpler. It's cosine t if t is less than pi. Then it's 5 plus 6 cosine t if pi is between pi and 2 pi, because negative 5 cosine t minus pi is the same thing as plus cosine t. And then lastly, that's cosine t, that's cosine t, or so it'd be just 1 plus 5 plus 5, 11 cosine t, if t is greater than or equal to 2 pi. So this mess on the top can be written somewhat more simply by writing it in terms of pieces. Now, I wouldn't necessarily expect this on the exam. If you were to write this as your final answer, that would certainly be all right with me, but just wanted to point out that this could be simplified by writing it in pieces.